Let's get the screen and I'll write it out. Just because you're saying this, let me sort of show it. Whiteboard. Can you all hear me and see the whiteboard? Can you all hear me? And
yes,
see the
sir.
whiteboard?
Yes, sir. Yes, sir. Yes, sir.
So see, you have a sample in the beginning. The sample is characterized by two things. What are the two things? It is characterized by an activity or enzyme activity, if you want to call it. And enzyme activity is, let us say, X units, XIU. I'm going to use X. I mean, I'm not going to mollycoddle you. You're not MSc students. I would write 1000 IU or something. It is characterized by the total amount of protein, total protein, which may be, say, Y milligrams. Now notice that total protein is Y milligrams, total activity is X units. So now there's one more point that I have to mention, and which is not known. But let us say that out of this total protein, the desired protein, which is the actual protein of interest, is actually, this is started giving problem right in the beginning. Oh God, sorry. This is really problematic right from the beginning. But let us see. Oh my God, it is frozen. My God, this is now going to create trouble. Hold on. The laptop started giving problem right in the beginning. No, it's frozen completely. I can't write, I can't do anything. This is a problem. Something has gone wrong. You'll have to give me a couple of minutes, try to get this laptop to reboot. Oh my, can you hear me?
Yes, sir. Yes, sir.
Yeah, you can hear me and everything, but the screen has hanged. I'll have to wait for a minute. Control Alt Delete, no games. Just a minute. This is not going to be nice. Can you hear me and see me? Hello?
Yes, sir.
Okay, so let the desired protein be Y. Notice this is small y milligrams. So now by definition, the specific activity of the pure protein, which is a fixed number of the pure protein, is by definition, this is also a property which you cannot play around with, is actually X upon Y. Right? And remember that therefore, because you know this specific activity from literature, it is already known. I mean, because any protein, from literature, you can know what is the specific activity of a pure protein. Okay, then from this, if you know this, and if you know X, then you can calculate Y. Y can be calculated. A small y is nothing but the known specific activity of the protein, which is a fixed number, divided by X, which divided by X.
No, sir, it is other way around, sir. Y is equal to X upon specific activity of protein.
So Y is equal to X upon specific. And therefore, if you know Y, you also know the percentage purity. Your percentage purity is actually nothing but Y upon Y. Right? Are you getting this? Now, when I purify,
Yes, sir.
When I carry out any purification, this Y will change. And any purification will get rid of protein. So you will get something called Y star, which will be less than the original Y. And so as we keep purifying, you will get lesser and lesser proteins. Are you getting this argument? And the idea is that this slowly becomes lesser and lesser to some y. And if I have three-step process, and finally this possibly may be equal to small y. Get my point? So
yes, sir. But sir, there may be some loss in
now
small y also.
assume that recovery is 100%.
Okay.
Assume that recovery is 100%, in which case all these will have activities of x and x and x and x and x. And therefore you see that the protein has been completely purified. This is the ideal situation, completely purified and no loss. So recovery is 100%, purity is 100%, because the protein has slowly become equal to y, and this has become equal to this. Now, unfortunately, this is no longer not true, because x is usually higher than x star, is usually higher than x double star, is usually higher than x triple star, which is usually equal. Let us say this is the final situation, which is the final yield. So your actual recovery is nothing but x triple star divided by x. So your recovery is actually x triple star by x, which is a percentage recovery or fractional recovery, and your activity is y triple star by x. So to that extent, even if your protein amount is equal to y, the original amount, your percentage purity is actually not yet achieved, because actually you have lost some of the desired protein. You understand? So your desired protein is y, but because a certain fraction of this has been lost, so if you want to have pure protein, your total protein in the final sample y triple star will have to be less than y. You understand? Because some of the y has been lost. They can be equal to this and yet have pure protein only when recovery was 100%. If recovery was less, which is given by this divided by this. So remember that really your x triple star divided by y triple star, which is the specific activity, should be equal to the true specific activity of the pure protein, which would have been given by x by y. Right.
Sir, I want to ask here one question. Like you said,
Yeah,
x would be less than x star, and it will be go on decreasing. Enzymatic activity would go on decreasing. But sir, enzymatic activity is of only one protein, that desired protein. So if the recovery is 100%, so why would enzymatic activity would change?
It will not. That is what I've been saying. I've not even listening. I said that this should be equal to this, should be equal to this, should be equal to this if recovery was 100%. I said that.
Okay, sir.
But you heard me, right? You were not hearing carefully. But unfortunately, in real practice, these are lesser. And these represent the recovery percentages. And this reduction represents the increasing purification. Because your total protein amount is being reduced. And the selectivity is a measure of the fact that this decreases faster than this. So at every point, the specific activity of the sample is given by x by y and x star by y star. Sorry, let me rub it out here and write it carefully here. So at every point, the specific activity, I'll write it here, is given by x by y and x star by y star and x double star by y double star, and so on and so forth. And notice that x by y is the specific activity of this sample, the specific activity not of the pure protein but of the sample, which is of course lesser than the pure protein x. So interestingly, this will be less. Now this has higher specific activity because the reduction in x to x star, this is the recovery, but this is the reduction in protein, but you have got more of contaminants and less of desired protein. So the reduction in X is less than the reduction in Y. And because the denominator has reduced more, therefore this number is higher than this and this number is higher than this. So purification proceeds like this. Y is greater than Y star is greater than this and this. And this increase is very, very high. Of course, there is recovery losses and this is lower. But the division of these two, X upon Y, I mean, as a matter of fact, if I were to put, makes no sense, but if I were to divide these, then these are higher. Or rather, actually, to make more sense, X by Y is less than X star by Y star, is less than X double star by Y double star, and so on and so forth. And so you can end up with pure protein, which would have an activity of X triple star by Y triple star, which may well be, if you are very good at purifying, which may be well be equal to the original X upon Y. This may well be equal to. This does not mean that this X is equal to X triple star and this Y triple star is equal to Y. Obviously, X triple star is less than X, but Y triple star is also less than Y. So you have not isolated all the protein. You have isolated only a fraction of the protein, which is given by recovery, but you have managed to get pure protein because you've got rid of all the contaminants. Is it clear now, the trade-offs?
Yes, sir. Yes, sir. Yes, sir.
Are all of you clear about this? Okay. Shall we stop here? This is simple algebra, but the concepts are important.
Yes, sir. So, sir, what would be the final relation between specific activity and recovery?
Tell me.
Sir, what can be the final relationship between specific activity and recovery?
Think.
Sir, specific activity would be greater than.
इतना algebra बीटेक स्टूडेंट्स नहीं करेंगे तो क्या करेंगे आप लोग? आप एमएससी के बच्चे नहीं हैं.
Yes, sir. Sir, आपने कहा कि sir ये X star, this represents recovery. This X star means.
Yes.
So if we take so if we take Y star here, so Y star X upon Y becomes specific activity, and Y star becomes
this divided by this becomes a specific activity. This thing here.
So this becomes
can be used to calculate a specific activity.
Relation and becomes recovery.
Yeah.
Recovery is greater than specific activity into Y star.
Yeah. I'm going to stop here. ये मतलब मेरे से algebra मत करवाइए आप लोग class 11th वाला है ना मतलब this is something which is more to do with the concept rather than the maths. Is the concept clear to you? You should be able to do the maths on your own. Yeah.
Yes, yes.
I mean, I believe that you are bright people. You know, we are bright people, and let us not. I will not do the algebra. I have a very strong decision. I don't do it for MSc students. I will not do it for you guys. I mean, I will not sit and do class 11th, 12th maths. This is something I will explain the concept to you. You go back, sit down, put numbers. Put numbers if you are not very comfortable with X and Y's. And put numbers here, put 100 milligrams and then 90 and 80 and 60 and put 200 units, 150 units and so on and so forth and see how it changes. See, make a table. Or I will ask Arunakshu to give you a table of activities and proteins and ask you to calculate recovery, percentage purity and so on and so forth, fold percent purification, etc., etc. Okay, so remember that the fold purification is this divided by this whole thing divided by this whole thing. So X star by Y star divided by X by Y is actually, why did I rub it? Oh, I put rubber here, sorry. So the fold purification in this step, in this step, the fold purification in this step is simply given by fold purification FP is equal to X star divided by Y star divided by X by Y. Okay, so this is the fold purification. So this is FP1, this will be FP2, this will be FP3, and the fold purification, total fold purification will be, this is FP1, FP will be equal to FP1 into FP2 into FP3. Okay, अरे फिर गायब हो गया. Can you hear me? Hello?
Yes, sir. Yes, sir. Yes, sir. Yes.
FP1 into FP2 into FP3, whatever. This is the total fold purification. FP1 into FP2 into FP3. Where FP1 is this divided by this, FP2 is this divided by this, FP3 is this divided by this. So obviously the fold purification is equal to this divided by this. Okay? The net fold purification is this divided by this. Obviously, you get my point? Each step, this is the fold purification. Right?
Yes, sir. Got it. Got it.
Oh, got it. Fine. So this is some simple algebra. आप लोग खुद करिए. Now, let us get back to more tough stuff. Now, I was talking about the fact that the mRNA to the polypeptide, and we'll talk about polypeptide to the protein later on, which is also a very interesting subject by itself. But that's back to genetic engineering. But this step, this translation step, is highly energy intensive and requires, and this is the step which requires highest energies and highest energy molecules means everything, means ATP, means and that in turn means better oxidative phosphorylation and so on and so forth. So this is a complicated step. Oxidative phosphorylation has to take place because that is what will generate my ATP. And then, of course, so the ATP machinery has to be highest. The ribosomal RNA machinery itself has to be high. The synthesis of ribosomal RNA, the content of ribosomal RNA has to be high. I hope you have done some amount of structured modeling which tells you that rRNA is high only when mu is high. Higher specific growth rates lead to higher rRNA levels, higher ATP levels, higher oxidative phosphorylation are all correlated with mu. All of these are positive correlations of mu. As a very simple example, they are equal to K into mu. It's a bad, I mean the worst model, but the most simple model ever possible. Okay, so as mu increases, if you look at rRNA synthesis genes, if you look at ATP, if you look at oxidative phosphorylation rates, usually the graph is like this. You know, different genes would have graphs like this, but they would all be positively correlated. Yeah, I mean, I'm as I said, I don't want to get into structured modeling, so these are graphs like this, which really means that translation is clearly correlated to mu. And this tells me two things, that if I want, and as I said, that if your transcription is by good promoters, etc., it is usually this step which often becomes the rate controlling step in protein synthesis. What does this tell you? It tells you that you need to keep mu high, because this is the rate I will get, and this is the rate you will get, and this is the rate you will get. So if you want high rates of protein synthesis, which obviously you want, and now because high rates and because of protein synthesis, and because you now know that protein synthesis is now being controlled by translation, okay, then obviously QP, because QP is your rate of product formation, which is nothing, which is defined by 1 upon x dP by dt, where P is your product or protein of interest. This is a function of mu and something like this. And therefore, in the simplest model, people write QP is equal to K or alpha mu. You have heard of this expression? What does this expression mean? Hello?
Yes, sir.
हाँ, इसको क्या बोलते हैं? This expression, the simplest that biologists could think of, that QP is proportional to mu. This is a straight line, approximately, and therefore QP, which is defined by rate of product formation, is a function of mu. And if this function is simply can be written as K into mu, then such functions are called, have a given name in biology. Biologists call it growth associated product formation kinetics. Have you heard this term?
Yes, sir.
So growth associated product formation kinetic means nothing but that QP, the rate of product formation, is proportional to mu, which or rather is equal to K into mu. If there is a linear proportionality between the rate of product formation and mu, then such products are called growth associated products. Okay, you have heard this term? No. Yes.
Yes, we have
सुना है,
heard.
भूल गए हैं, सुनाई नहीं है, क्या मतलब, कुछ तो बताइए. हेलो.
We have heard, sir. We have
We have heard.
these
So
were
we have heard. There are 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 people, and you have done a course in bioprocess and you have not even heard of this term, then it's a problem. अच्छा, सुना है, लेकिन you did not know that this is what it means. This is what it means. आप लोग में से कोई बंगाली है? 21 लोगों में से, जैसे मैं हूं? नहीं. Bengali log, they are a very strange, Bengalis are a very strange class of people. They call each other as Bengalis and everybody else as non-Bengalis. I mean, after all, they will not call them Gujarati or Maharashtrian or Punjabi or Tamilian or whatever. They will lump all of them together as non-Bengalis. This is a very, 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 very superior sort of attitude, which is a problematic, which is born out of ignorance. But everybody else, we don't need to understand them. They're all non-Bengalis. Similarly, everything, biologists have this very silly attitude. If QP is proportional to mu or equal to K into mu, then it is growth associated product formation kinetics, and every other relationship of QP is equal to a function of mu, any other non-linear relationship, including the fact that QP is equal to beta, which is a non-function of mu. So if it is not growth associated product formation kinetics, then it is non-growth associated product formation kinetics. That's a nice word, and that is how biologists used to work. We now understand much better as biochemical engineers, non-growth product formation kinetics. So everything is very simple for biologists. It is either growth associated kinetics, which means QP is proportional to mu, and otherwise it is non-growth associated product formation kinetics, which is QP is not proportional to mu. What it is, no need to explain. Okay, so these are simplistic notions, but I hope you realize why they had such simple notions. Because remember that if QP is proportional to mu is equal to alpha mu, then remember QP is 1 upon x dp by dt, and this is 1 upon x dx by dt. So if they are proportional to each other, equal to alpha into this, let us say, then as you can see, dp by dx is equal to alpha, which this dp by dx is nothing but also can be defined as yp by x, the product formed per unit biomass. So what you are trying to say is that yp by x, the product formed per unit biomass, is equal to a constant. Which means that if the biomass increases from 1 gram per liter to 5 grams per liter, and the product is 0.1 gram here per liter, then the product will become 0.5 grams per liter. So there is a proportionality which is maintained. Yp by x is 0.1, and so if you make 15 grams per liter of biomass, you don't have to do too much of calculation. You multiply it by 0.1 and say there will be 1.5 grams of product. You don't have to solve this differential equation at all, because proportionality will always be maintained between the amount of product and the amount of biomass, because yp by x is equal to alpha is equal to a constant. If such proportionality is not maintained, that is, the amount of product formed is no longer proportional to Can you hear me?
Yes, sir.
This proportionality is no longer true. Product formed is not proportional to biomass. Then sorry, it is non-growth associated. If product is proportional to biomass, growth associated. Product is not proportional to biomass, non-growth associated. So it makes sense, right? The process of product formation, if this is the biomass growth, the process of product formation is is linked intimately to the growth process. This could be when product is like recombinant protein, but it could well be when the product is a product, because product is, what is product? Product is not something which the cell defines. Product is defined by you. है ना, आपको क्या चाहिए, क्या चीज आप बेच रहे हैं, है ना? So the product is defined by you. So the product, if it is an intrinsic component of the cell, for example, nowadays with DNA vaccines, plasmid can be a product. You can sell plasmids. You need not sell proteins. Plasmids are being sold because people want DNA. And the plasmid can be, the DNA can be inserted in the plasmid of your choice, and then the cell can be grown. But if the copy number of plasmid is fixed, let us say it is 100 or 200 or whatever, or 200 or whatever, then the number of copies of plasmid per unit cell is fixed. And if the copy number of the plasmid is fixed, then the amount of plasmid that you will make per unit cell is fixed. So Yp by X is a constant. So by definition, it is a growth associated product, because it is an intrinsic component of the cell. The product is defined by you, and plasmid is the product, and 100 or 200 or 300, whatever is the copy number, is the amount of product that you have made. So you make more biomass, you will make more plasmid. Suppose 10% of the cellular biomass is plasmid, or 1% or 2%, very unlikely to be 10%, so maybe 1%. 1% of the cell is biomass, so 15 grams, 0.15 grams, 5 grams, 0.05 grams, 1 gram, 0.01 gram, and so on and so forth. So if it is an intrinsic component of the cell, or it, like recombinant proteins, it is formed in the same process as cell biomass forms. And remember, translation is one of the most important energy consuming central step of all growth. Translation and the making of proteins is a most important component of all growth processes. It consumes the maximum energy, it occupies the maximum space inside the cell. Proteins occupy 50% of the total mass of the cell. So translation, turnover of proteins, is the most important reaction that is happening inside the cell, if I can call it a reaction. Right? And it is consuming the largest amount of cellular resources. So it is an intrinsic component of growth, and the same translation which causes growth also makes my product, which is, because now my product is defined as the recombinant protein, and hence this also becomes growth associated. Is this clear to all of you?
Yes, sir.
Yes, sir.
Okay. So now, what are the implications of this for a biochemical engineer? For biologists, you will be told that please induce in the log phase, otherwise you will not get protein. But for the biologist, biotechnologist, you are now trying to grow the cell in a bioreactor. Now, how do you maximize growth? Remember, you cannot do continuous bioprocessing, because you cannot use a CSTR or any continuous bioprocessing because of the issue of plasmid instability. So continuous bioprocessing is almost impossible for recombinant processes. People have been trying very hard, but it seems to be a difficult thing to achieve, because as I pointed out, in any CSTR, the moment plasmid-free cells emerge, the system will become unstable very fast. So obviously the other options are batch and of course fed batch. Why fed batch? Yes, why fed batch?
For aiding sometimes aiding nutrients and other
Yes,
materials.
and also if you can add nutrients slowly in the feed, you can actually make larger amount of biomass. But the more the biomass, the more the product, right? Per cell, if the productivity is something, the higher if this is high, hopefully this will be high. But remember that not only this has to be high to make more product, because of the correlation with mu with QP, then a high mu will reach a higher QP. A low mu will be having a low QP. So you will make very small fraction. So you want to make Yp by X or whatever high, you better have a mu of high value. So the optimum mu is usually high, is pretty high, is high. I mean, if you make mu even higher, then QP may fall for reasons like acetate overflow mechanism, glucose overflow mechanism. ये सब आप लोगों ने सुना है? Glucose overflow वगैरह? No? Yes?
No, sir.
No, sir.
We are going far away. But remember that glucose is being consumed, and people in microbiology, they call it the Crabtree effect. But those are, as I said, definitions and not real biochemical engineering. But here is the pyruvate node. And then, of course, I mean, my biology is very poor. And then this acetyl CoA and so on and so forth. You remember all this stuff? And then, the TCA cycle.
Yes, sir.
Yes, sir.
And then from the TCA cycle, the electron transport chain and so on. Yeah, it is not etc. Electron transport chain and oxygen and so on and so forth being required, and CO2 being generated and so on and so forth, and ATP being formed and so on. And these steps, now this step is fast if you supply more glucose. It is controlled by the amount of glucose available. And these steps, TCA cycle, electron transport chain, these steps are slow, leading to accumulation of pyruvate. And if this sort of accumulates, where will it go? It will go to the non-oxidative phosphorylation, which means it will go to acetic acid. And this acetic acid formation takes place, therefore, whenever there is excess glucose. And that is why in fed batch you have slow feed, so that the glucose levels or the carbon levels do not increase. Because this is a fast step, this is a slow step. So the cell sees food, it eats up. Like many of us. आलू चिप्स मिला, खा लो. फिर वो आलू चिप्स एक्चुअली मसल और एनर्जी में नहीं यूज होगा, वो तो पेट में जाके फैट बनेगा. लेकिन आप लोगों को अभी चिंता नहीं है क्योंकि आप लोग यंग हो, है ना? But when it becomes fat, similarly the cell gorges itself on glucose and then makes acetic acid, and that then actually reduces the pH and reduces product formation, and therefore this is the place where this is happening. So you don't want to go to higher mu's indefinitely. So for all practical purposes, till mu is equal to 0.3 or so, you would have a QP increasing with mu. So you want to hold the mu at a mu optimum mu of 0.3 our inverse or so. Right? Now this is the question that I want to, and beyond that, of course, there's acetic acid formation, so I don't want to do it now. There are more complex questions. For example, I talked about the CSR. The CSR slows this even more because this becomes slower. The CSR makes this slower. So acetic acid starts forming even at lower mu at 0.3 also, and so on and so forth. Let us not get into too much of complexity, but let us say that acetic acid does form at higher growth rates, and therefore, and yet we have QP proportional to mu. So we want to have an optimum mu which is very, very high. So let us get down to the bioprocess part of it now. What is the bioprocess part of it? You're all familiar with the bioreactor and a fed batch reactor. Obviously, I want to hold the mu at its optimum value this year. I don't want Crabtree effect, but I want the mu to be optimum, which really means I want to keep mu constant at the mu is equal to mu optimum. Correct? If now I want to make mu equal to mu optimum and I want to use a fed batch culture, what is the what kind of feeding should I do to keep mu equal to mu optimum and increase biomass? Because X has to be high. Remember, X has to be high. So one of the purposes of fed batch culture, and these are called high cell density cultures. So all industries would use high cell density culture to produce recombinant protein. But the point is not just HCDC. You can make a lot of cells, but also that these cells should be producing product given this equation here. So not only they have to be grown to high cell density culture, but at the optimum mu. So how do you make high cell density culture at optimum mu? How do you maintain mu at a certain value? By fed batch cultures. What kind of fed batch? Hello. The idea in biotechnology is not to forget courses once you have got the grades, but to remember them beyond. Yes, please. Reactions, responses. हाँ भाई कुछ आप लोग बोलेंगे? What is fed batch culture? Have you all gone away?
So we are
Using
That you are adding
exponential
the
fed batch
nutrients.
cultures.
Yeah, go ahead. One person at a time. So fed
So I
batch, you
guess
feed.
can use
Yeah.
the exponential
You
fed
guess.
batch
I mean, it's
culture.
not. Yeah. Sorry. Yeah. Go ahead. So
Can we use
what they
like
do?
fed batch cultures
Yeah.
with exponentially increasing flow rate?
Feed. Absolutely. So,
Yeah.
so really, the batch, once it is over, let us assume that the batch is over, then, and let us say that because I don't want to increase the volume tremendously, and I don't want to increase the volume too much in an industrial reactor, so I will use concentrated feed. I will use concentrated feed. So for example, okay, we will do the numbers. Let me actually solve a problem, right? And that I think should resolve everything. So you use a concentrated feed because you don't want to increase the volume too much. And the concentrated feed allows you to increase the biomass concentrations a lot. X increases, but X and X I will treat as same by assuming that the volume changes are negligible. These are approximations because I don't want to do irritating mathematics here. So now my feed is F and my substrate feed concentration is SF, and SF is very, very high. Remember, for example, that in the initial part of the fed batch, you grow the cells in batch. And when you grow the cells in batch, you have a substrate concentration S in the start of the batch, S batch or S start. Now, this S batch cannot be too high, but SF can be as high as possible. S batch, and let us make very, very crude assumptions quickly so as to make life easy. S batch, for example, is 10 grams of glucose, plus of course nitrogen sources and magnesium and everything else, or maybe 20 grams. And let us say that, for example, Yx by S, the biomass yield is 0.5. And if S batch is 10 grams per liter in the beginning, at the end of the batch, how much will be the biomass approximately? What will be the biomass at the end of batch? All the substrate will be consumed. So the basic equation that you write for batch cultures with biomass balance is a simple equation. Is that I hope you remember this. X is equal to Y S naught initial concentration minus whatever S residual concentration plus X naught the initial inoculum. Now let us assume that this is approximately equal to Y S naught. अगर ये negligible हो गया, ये 10 ग्राम से शुरू किया आपने और मान लीजिए कि एंड हुआ 10 मिलीग्राम में, तो 10 ग्राम माइनस 10 मिलीग्राम इज 10 ग्राम, और मान लीजिए कि इनोकुलम साइज भी बहुत छोटा है, तो इट्स इक्वल टू वाई यू नॉट. सो लेट अस से इट इज इक्वल टू वाई एक्स बाई एस into S naught, which suppose Yx by S is, let us say 0.5. If Yx by S is 0.5, then by definition, and S naught is 10, then this is equal to 0.5 into 10, which is equal to 5 grams. So your biomass is 5 grams per liter, which is very small. But that is very important. FSF. Now this SF part of it could well be 200 grams per liter. Because I'm going to feed it slowly, so I don't have problems of Crabtree effect or any such thing. Or 300 grams per liter or 400 grams per liter. And I can feed concentrated feed slowly. And as I feed, this biomass will increase from 5 grams per liter more and more. So once this batch is exhausted of substrate, I start the substrate feed such that this substrate feed will allow the biomass to increase. Are you getting this?
Oh, yes, sir.
Yeah. So now let me sort of rub it out. So really now it's simple enough. So now let me get down to the basics. Now typically ds by dt, the rate of change of substrate concentration in the fed batch, is equal to FSF minus mu x by yx by s. I'm going to simplify it. I'm not going to write very complicated equations. And this is the accumulation or disaccumulation of substrate inside. And I do not know whether you remember the quasi-steady state assumptions, QSS of fed batch. Essentially, they say that this is zero because the substrate concentrations are small and they change very slightly. So therefore, this implies that the feed rate FSF is equal to mu x by yx by s. Really what I am saying is very simple. I am saying that this is my feed, this is my biomass, and this is my feed with the substrate concentration SF. And what is happening is that the increase in biomass that is taking place is only because of this substrate. And all the substrate that gets added, that is falling dropwise, is immediately consumed. Okay, got the point? That cells are starving more or less. They're very efficient consumers of substrate. So FSF is equal to mu x by yx by s. So this is the growth rate. So this is the consumption rate of substrate and this is the supply. So supply is equal to consumption. There is no accumulation and obviously there is no outflow. Everything that is supplied is eaten up. It is a starving population. Because, or a very efficient utilizer of substrate population. Cells are very efficient utilizers of substrate, by the way, and because as is evidenced for the fact that when you write mu is equal to mu max s upon ks plus s, these ks values are very, very small. For E. coli, they are in the order of few milligrams, 10 milligrams per liter. So such low values, the mu falls only to half the value. These low values of ks are proof that they are very good scavengers of substrate. Right. So they are consuming it. So the effective concentration here is of the order of a few milligrams, close to Ks. So everything is consumed because you are supplying 200 grams. You are supplying, as I said, 200 grams or 300 grams per liter, grams per liter, not even milligrams. So it is falling dropwise. The concentration is increasing and immediately it is being consumed. So there is no change in concentration. ds by dt is equal to 0. S is low and constant. And we have the substrate supply and the basic material balance equation of substrate is this equation. And of course, if you want cells to grow exponentially and mu to be a constant, then FSF is equal to mu, and I'm going to jump a little bit of mathematics. This is easy enough for you. Mu is a constant, and if mu is a constant, x is some x naught at the start of batch, e raised to mu t. Right? Divided by
Yes.
Now let us jump a few steps and not solve differential equations. Let us do it quickly because we are running out of time. And therefore, by definition, given a certain QS, by definition, your F becomes equal to mu x naught e raised to mu t divided by yx by s SF. So notice that of these things, mu is a constant, x naught is the value that you achieve at the end of batch. X naught is end of batch, which was 5 grams. End of batch is x naught. So that is where you start the feed. And yx by s is known to you. SF is of course known to you. So these 4 things are all constants. So F is equal to F naught e raised to mu t, where F naught where F naught is nothing but mu x naught yx by s into SF. Right? Are you getting this? So, for
Yes.
example, if I put,
Yes, sir.
and let me put numbers just for, I mean, though I should not, if people should be able to handle it, but still for convenience. So, if, for example, we take the previous example, what was it? I took S batch was 10 grams per liter. So X naught would become approximately 5 grams per liter. And suppose I said SF is 200 grams per liter. And let us say that the mu optimum is 0.3. Then by definition, F is equal to 0.3 into 5 grams e raised to of 0.3 t divided by yx by s is 0.5 just now, and SF is 200. ठीक है ना? ये हो गया, क्या हो गया भाई? 0.55, ये 10 हो गया ना? 0.3 by 20, right? 0.3 by
Yes.
20, and let me choose the volume as 1 liter, है ना? जिससे कि x और x सेम हो, है ना? मतलब approximately at any, मतलब 1 liter volume, मतलब मैंने, I forgot to choose the basis of the reactor volume because without choosing. So in a 1 liter reactor, if this is a 1 liter reactor, my feed should be 0.3 by 20. कितना होता है भाई?
0.015.
अच्छा, इसको 0.015 liters per hour, which is equal to 15 ml per hour. So a concentrated feed of 200 grams per liter of glucose with additional amounts equally concentrated will be fed at 15 ml per hour, will be started at 15 ml per hour and will continue to be increased with the function which will be given by F is equal to 15 ml per hour e raised to of 0.3 t ml per hour. So for example, after 2 hours or 3 hours, what will be the feed? Well, let us do this very funny calculation. I mean, I do it for biologists. You can of course substitute it, but I do this very simple thing, which I call that, if the cells are growing at 0.3, then the doubling time TD is given by, and I hope you know this, I don't want to do this, ln2 by mu. All of you are familiar with this equation and its derivation?
Yes,
Yes,
sir.
sir.
Yes.
Yeah, so TD becomes equal to 0.693 divided by mu, which is 0.3, which is equal to कितना हो गया ये? 2.3 ना? पता नहीं जितना भी होता, 2.3 hours. So if I were to make a chart, I mean, of course it will be, then I would have this following situation. Time, when time is 0, feed is equal to 15 ml per hour, and I know that at 2.3 hours approximately it will become 30 ml per hour, and at 4.6 hours it will become 60 ml per hour, and at 2.6 में जोड़िए कितना होता है? 6.9 hours it will become 120 ml per hour. So obviously my feed is this. Of course, it is not in steps. It is actually a feed like this, which has an equation given by this equation. So this is my feed, and it goes up like this. And obviously, biomass also goes up because this is 5 grams. At this point of time, the biomass X here was 5 grams, and it's 5 grams, and at this point the feed is 2.3. When feed is 15, the biomass was 5 grams. At 30, the biomass is 10 grams, and at 60, the biomass is 20 grams, and this is 40 grams. Notice that 5 grams required a 15 ml per hour feed, 10 grams requires a 30 ml per hour feed, 20 20 grams requires a 60 ml per hour feed and 40 grams requires a 120 ml per hour feed, which really means that cells are growing exponentially. They are being fed in proportion to the biomass. So the biomass increases exponentially, the feed increases exponentially. And at some point, because this cannot be sustained forever, you decide that at this point here, you decide at some point that you will, can you hear me?
Yes, sir.
Yes, sir.
Yes, sir.
At some point, you will decide that I will induce the culture. Because, so I will induce the culture, let us say at 20 or 40, and at this point I will induce the culture. Why? Because biomass has already increased a lot, I cannot increase feed indefinitely. Why cannot I increase feed indefinitely? Because as I'm increasing feed and all of it is being consumed, my oxygen demand, oxygen uptake rate demand is also increasing. And OTR is also increasing. And OTR is given by KLA C star minus C. And I cannot reduce C below a certain value. After I cannot starve the cells of oxygen. And so my KLA determines the OTR because C minimum, some minimum value that you need to maintain. And so that fixes the OTR, that fixes the OTR max, that fixes the OUR, and that OUR fixes this maximum value. Because feed, whatever it is, if it is making biomass, exactly in same proportionality, OUR and OTR will also be increasing exponentially. Right?
Yes, sir.
But after all, there is something called Yx by O, na? Which is also a constant. And we can derive it by stoichiometry. I hope you would have done it in the course, in your bioprocess course.
Yes, sir.
So
Yes, sir.
your oxygen demand, as X increases, your oxygen demand also increases because your dx by dt is increasing, right? Because it is equal to mu into x, and mu is a constant and x is increasing. So x is also equal to x naught. So everything is increasing exponentially because, as you all know, that derivative and integral of exponential function is an exponential function. So OUR is also increasing exponentially, OTR is increasing exponentially, and you will soon reach a limit of oxygen availability. And there you are in trouble. So you cannot increase oxygen, so you have to induce the culture. And the later you induce, the more biomass you have. And that is why you can make more product. So this is the problem. So we'll talk about this in the next class. Thank you. I think we're already overshooting time.
Sir, when we will start enzyme kinetics?
Thank you, sir.
जितनी जल्दी आप मुझे ये खत्म करने देंगे, मैं कोशिश करूंगा कि by this week itself I will finish. I mean, enzyme kinetics is a huge course, and I know I will not teach many things, many complicated stuff, especially the algebraic models, because they are very tedious. But I will try to teach you more than simple enzyme kinetics, and I hope you realize that that's a bit tough. So I don't want to compress enzyme kinetics anymore, but I need to do justice to the production process. And if you people keep saying that हमको fermentation नहीं आता, fed batch नहीं आता, तो फिर मुझे ये detailed करना पड़ता है. नहीं तो मैं तो एक second में बोलता कि भाई this is exponential fed batch, and you can well imagine that that has a limit with the OUR, and that is its job done. But if I said this, I am not very sure how many of you are confidently able to understand that this, what I have written now, is what I meant by that single sentence. Or are you familiar with all this stuff?
Sir, we are familiar with all this stuff, oxygen uptake rate, oxygen transfer rate. Sir, but I'm
do
saying
you
that
understand the relationship with exponential feeding and the relationship with increasing enzyme production? So if I give you a problem that this is my KLA, please determine how much enzyme you will produce given QP is equal to this. What is the maximum enzyme you will produce? Can you solve that problem? We will do that problem on Friday, and let me see if you can solve it. Okay?
Yes, sir. Sir, I was saying
Let
that
us do it in the class. I mean, I don't want to give it in an exam without actually knowing that you can solve it or not. My problem is, as I said, that each and every subject has huge depth, which I cannot explore, and my lack of knowledge or information about how much you remember from previous courses. These are the two things that I am fighting against all the time. So you have to excuse me if we tend to sort of oscillate a bit and go to enzyme kinetics a bit late, because I need to do justice to this subject. I of course
sir,
want to do
but the weightage of enzyme kinetics would be more na in the exam.
जैसा आप चाहेंगे, whatever you want. Yes, but
Okay,
not in
sir,
the
okay,
midterm.
sir.
Not in the midterm, in the end semester, of course. Yeah. Thank you. Thank you. You have a next class.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.